Welcome to Chapter 9 of Class 8 Science, the Amazing World of Solutes, Solvents, and Solutions. In this fascinating chapter, we'll explore why some substances mix perfectly while others don't, how temperature affects dissolving, and why objects float or sink in liquids. We begin by observing everyday examples: the sugar in your tea, the salt in your food, the ORS you drink when sick, and learn to classify them based on their uniformity and composition. Get ready to discover why every sip of ORS tastes the same, how temperature affects solubility, and what makes water the universal solvent. Let's begin by understanding uniform versus non-uniform mixtures. Have you ever taken oral rehydration solution and wondered why every sip tastes exactly the same? This happens because when you add sugar and salt to water, they form a uniform mixture where the components are evenly distributed throughout. In contrast, when you mix chalk powder or sand with water, the components are not evenly distributed, creating a non-uniform mixture. A uniform mixture is called a solution, and it consists of a solute dissolved in a solvent. Understanding this distinction helps us understand everything from cooking to medicine preparation. Now let's explore the components of solutions in detail. A solution has two main components: the solute, which is the substance that dissolves, and the solvent, which is the substance that does the dissolving. In solid-liquid solutions like sugar in water, the liquid is always considered the solvent regardless of the amounts. Interestingly, even air is a solution, with nitrogen as the solvent and oxygen, carbon dioxide, and other gases as solutes. The gulab jamun syrup is another fascinating example where, despite having more sugar than water, water is still considered the solvent. Understanding these components helps us predict how substances will behave when mixed. Let's investigate solubility limits through saturated and unsaturated solutions. Have you ever added too much sugar to your tea and noticed that some sugar remains undissolved at the bottom? This happens because every solvent has a limit to how much solute it can dissolve at a given temperature. When a solution can dissolve more solute, it's called unsaturated. When it has dissolved the maximum amount possible and some solute remains undissolved, it's called saturated. The concentration of a solution tells us how much solute is dissolved in a fixed amount of solvent. Understanding these concepts helps us prepare solutions with precise concentrations for various applications. Now let's explore how temperature affects solubility. You've probably noticed that sugar dissolves faster in hot tea than in cold water. Temperature plays a crucial role in how much solute can dissolve in a solvent. For most solids, solubility increases with increasing temperature. This is why we can dissolve more sugar in hot water than in cold water. However, for gases, the opposite is true: solubility decreases with increasing temperature. This is why cold drinks go flat when warm; the carbon dioxide gas escapes. Understanding temperature effects helps us in cooking, medicine preparation, and industrial processes. Let's discover why water is called the universal solvent. Water can dissolve more substances than any other liquid, making it essential for life on Earth. This special property comes from water's polar nature. Water molecules have positive and negative ends that can attract and surround solute particles. Water dissolves polar substances like salts and sugars well, but doesn't dissolve nonpolar substances like oils and fats. The principle, like dissolves like, explains why salt dissolves in water but not in oil, while turmeric dissolves in oil but not in water. Ancient Indian texts show advanced understanding of water purification using natural materials. Now let's explore density and buoyancy, why objects float or sink. Have you ever wondered why a heavy ship floats while a small stone sinks? The answer lies in density, which is mass per unit volume. Objects float if they are less dense than the fluid they're in, and sink if they are more dense. This is explained by Archimedes' principle. An object experiences an upward buoyant force equal to the weight of the fluid it displaces. In our egg experiment, we see that an egg sinks in plain water but floats in salt water because salt water is denser. Understanding density helps us design ships, submarines, and many other technologies. Let's explore real-world applications of solutions and density. These concepts have numerous applications in daily life, from medicine to transportation to environmental science. ORS for dehydration uses the principle of isotonic solutions for quick absorption. Ships are designed to displace enough water to float despite their heavy weight. Submarines use variable density by taking in or expelling water to sink or rise. Hot compresses use supersaturated sodium acetate solutions that release heat when crystallizing. Traditional Indian preparations like panchamrit show practical understanding of solution chemistry in daily life. As we conclude this chapter, let's review the key concepts and their importance. We've learned about solutions as uniform mixtures of solute and solvent, understood solubility limits through saturated and unsaturated solutions, explored how temperature affects dissolving, discovered why water is the universal solvent, and learned why objects float or sink based on density. This knowledge helps us understand everything from cooking to medicine to transportation. Remember that solutions are all around us, and understanding them helps us understand our world better and develop innovative technologies that improve our lives.